So on the right-hand side, there's a molecular dynamics simulation of a lipid bilayer. So the molecules shown in red and white on the top and the bottom are water, and so these are bouncing around here. And then on the inside, these are lipids, which comprise the lipid bilayer. So these blue parts are, for instance, the hydrophobic tails. So if we take the water away, we can look, and from a bird's eye view, we can sort of look at the motion of, for instance, one lipid, which is shown here in red, and we can see this traverses through the membrane. So it can move through the membrane left and right, up and down through the membrane. So again, we're looking at the top of the membrane at this point and just looking at one particular lipid, which is shown here in red, and that's shown in a blue background here. Okay, so the idea of this shows that, what this shows is that the membrane is fluid in some context. So lipids within the membrane can move around to other parts of the membrane on the cell. So you can even think of, for instance, a lipid that starts maybe on one side of the cell, can migrate to another part of the cell. Okay? And so let's go back to let's go back and look at this. Oh no. Fast forward. Okay. Let's go back to this. So the idea is that again, the membrane is fluid. So lipids and also things that are incorporated into the membrane can move laterally across the membrane. But it's really hard for them to flip, for instance, from the outer leaflet of the membrane. So for instance, in this figure so let's start with the panel on the bottom. So this is lateral diffusion. So again, lipids and other things that are incorporated in the membrane can move within the leaflet they're in. So for instance, here is the outer leaflet on top, and then on the bottom is the inner leaflet, if we're thinking about the membrane of the cell. Okay, so a lipid can traverse very nicely and diffuse through the leaflet that it's already in. But however, to switch between the outer and the inner is much more difficult, and this is much slower and actually requires some enzymes in order to catalyze this transfer between the inner and the outer leaflet, okay, for it to occur at a normal pace or at a usable pace. So, but again, the fluidity really, what we're talking about when we're talking about the fluidity of the membrane has more to do with this lateral diffusion. And so depending on the composition of the lipids within a membrane, the fluidity of the membrane can be altered. So this can be dynamically altered depending on what sort of lipids are within the membrane. So for instance, saturated lipids. So remember when we talked about saturated fatty acids, something like butter is full of saturated fats. And this is more of a solid lipid, we know, because we get sticks of butter, right? Versus something like vegetable oil, which is higher in unsaturated fatty acids, unsaturated fats and polyunsaturated fats, is more liquid, okay? And so this is reflected in the melting temperature. So for instance, a 12-0, a lipid with 12-0, which is the general name is, or the common name is dodecanoic acid, has a melting temperature of 44.2. If we increase the carbon chain length to an 18-0, which is stearic acid, we also increase the melting temperature. So a higher melting temperature, so if we have a membrane filled with nothing but stearic acid, it's going to have a lower membrane fluidity than something that a membrane completely composed of dodecanoic acid, which has a melting temperature of 44.2. But we can also make the membrane can also be made more fluid by incorporating more unsaturated fatty acids, such as 18,1-del-9, which is oleic acid, or 18,2-del-9-del-12, which is linoleic acid. And those have TMs of -5 and -11 degrees C. So the lower, again, the lower melting temperature includes a larger membrane fluidity. And remember, this has to do with the kinks that are formed in the unsaturated, by the unsaturated fatty acids. So that spaces out the nonpolar groups, the nonpolar tails from each other, and doesn't allow them to pack quite as tightly. So they can't form very close pack interactions, and therefore they become quote unquote less solid or more fluid. If you're looking for more examples of this, there are several more of them in Table 9.1 inside of your book.